Hi guys, Alex here, and today I'm going to be teaching you about LZW compression, how it takes a string or list of numbers as an input, and then how it's going to compress it, and if it needs to, create its own dictionary. So what a LZW compression algorithm does is that it takes a certain amount of bits used to represent the information you're currently representing. So in our example, we're only representing numbers 0 to 7. So we're technically only using 3 bits of information. However, what we're going to do is we're going to need a dictionary of all the numbers that we're going to combine. So if we're going to combine 0 and 0, 1, well, we can't represent that with 0 through 7 because we're already using these. So we're going to use a bit extra, and we're going to use numbers 8 through 15, which we never plan to show in our list of string numbers or other data. So the way we start is we start at 0. And the rule of this algorithm is that I can never look behind me. I'm only allowed to go forward. So I look at 0, 0. Have I ever seen this number in my dictionary or list? No. So what do? I create my dictionary. So if I haven't seen it before, the most I can do is put the number itself. So I put 0, 0. I look ahead of me, since I am allowed to do that. I see the number 0, 1. I know that these might be in the list of numbers further. So what I do is I represent it in the dictionary. I'll use the first number available to me, which is 0, 8, since it's the first number at the beginning of our extra bit. I'll use the 0, 8, and I'll use it to represent 0, 0 and 0, 1. I move on to the next number. I move on to 0, 1. I have not seen 0, 1 in my dictionary, and so I have to put it in my compressed list. I look ahead, and I say, hey, maybe I will see 0, 1 and 0, 2 further in the list of numbers. So I save it as 0, 9 in the dictionary. And so I take 0, 1 and 0, 2. And this is all going to make a little bit more sense as we go. But basically, the dictionary is what we use to take two numbers and combine them into one. The next number that I move on to is 0, 2. I have not seen 0, 2 in my dictionary, and it's the first time I'm seeing it in my list. So I'm going to put it in my compressed list. The number ahead, which may or may not be in the list of numbers ahead, is 4, and so I'm going to represent that with 10. And that will represent the numbers 0, 2 and 0, 4. And so as I'm going, I'm creating a dictionary using an extra bit of all the combinations possible in my list of numbers, or at least sequentially. So I move on to 0, 4. It's my first time seeing 0, 4, and I can't find it anywhere in the dictionary. So what I'm going to do is I'm going to put it into my compressed list. And then I look at the number ahead, and I say that 0, 6 may be paired with 0, 4 later in the list of numbers. So I mark that as 11, and it represents 0, 4 and 0, 6. So to speed this up a little bit, I'm going to go a little bit faster. It's my first time seeing 0, 6 because it's not in a dictionary. And I write it down. I look at the next number. That's 0, 7. I'm going to save the combination of 0, 6 and 0, 7. That is 12. And then I move on to my next number, 0, 7. I look at 0, 7. It's not in my dictionary. So I write it down. I look at the number ahead. And I save it as a possible combination. And so that's 0, 7 and 0, 4. Okay. So I'm going to write that down. Perfect. And now I move on to my next number, 0, 4. Now here's the thing. I have seen 0, 4. It's in my compressed list already. I have seen 0, 6. So, if I go to my dictionary, I've seen 0, 4, and I've seen 0, 6. What number represents that? 11. And so, I'm going to write down 11 in my compressed list. And so now, I'm representing 0, 4 and 0, 6 as the number 11. I move on to my next number, 0, 6 and 0, 0. I've already written 0, 6, and so now I'm on 0, 0. I've seen 0, 0 before at the beginning of my list, right here. And so I look at the number ahead. I've seen 0, 1 at the beginning of my list already. And so I look to my dictionary. In my dictionary, 0, 0 and 0, 1 is saved as the number 8. So I write down the number 8. And so in this way, I've been able to combine two sets of numbers into 11 and 8, which is in that extra bit that we saved for us to use. I go on to my next number, 0, 3. I've not seen 0, 3 anywhere else in my list. And so, I'm going to write it down. And then, what this has done is this has effectively taken 0, 4 and 0, 6 and shaved them off by two numbers. And that's how the LZW compression algorithm works. Hi guys, so we just went over the LZW compression algorithm, and in this we took pairs of numbers and we always stored them in the dictionary, and then when we recognized that number in the dictionary, we took that pair and we simply used the dictionary alternative. So where we saw 0, 4, stored it in the dictionary as 11. We saw 0, 4 and 0, 6 again. We saw it in the dictionary and we represented it as 11. So now we're going to go over how the decompression for the LZW algorithm works. So let's take our compressed list of numbers. Let's move it down to here. And we're going to label this our compressed list. We're going to have our we're going to have our decompressed list. And then we're going to have our dictionary. And remember, in this example, we are using a 3-bit number system to represent the numbers 0 to 7. And then we are using 4 bits in total to represent the numbers as well, 0, 8 to 15. And we do this so we have space in the dictionary to write down combinations, and we use that to compress and decompress. So, this is our compressed string, and remember this is an algorithm where we only look forwards, and we can never look back. So, we start at 0, 0. We check to see if 0, 0 is in a dictionary. We don't have a dictionary. And we write down 0, 0 as part of the decompressed list. And we look to the number forward, which is 0, 1. We say that it may be in the list further on, and so we store it as a combination. And because we only go to represent the number 7, the next thing that it can possibly represent is 8. 8 will be the number that we cannot use, and so we'll use it for the dictionary. And 8 will represent 0, 0 and 0, 1. Then we move on to the next number, which is 0, 1. We check to see if 0, 1 is in the dictionary. It's not, because it's one of the numbers that is our base numbers. So we write it down in the decompressed list. We look to the number forward to see if we can make a combination, and we see the number 0, 2. We store 0, 1 and 0, 2 as the number 9. We go on to the number 0, 2. 0, 2 is not anywhere in our dictionary, and so we write it in the decompressed list. And then we look to the number forward to store the pair, and we see that 0, 2 and 0, 4 can be represented as the number 10. Okay, and now we go to the number 0, 4. 0, 4 has not been put in the list yet, and it has not been put in the dictionary. So we go to 0, 4, we put down 0, 4, we go to the number ahead, we say that it can be stored as a pair, and we represent that as the number 11. So we put 0, 4 and put 0, 6. Awesome. We'll go on to the next one. 0, 6 is not in the dictionary. Haven't put it in the decompressed list yet, so we put it into the decompressed list, look to the number ahead, and store it as a possible pair. So that's going to be 0, 6 and 0, 7, stored as the number 12. Awesome. We move on to 0, 7. We have not seen it in the dictionary, and so we'll put it in as 13. We'll look to the number ahead, and it stores 0, 7 and 11. Awesome. And we put it into the decompressed list. We move to the number forward. So now we're on 11. Well, we can only represent numbers 0 to 7 in our base numbers. And when we look at the dictionary, we see the pair 0, 4, 0, 6. So we're going to pull the 0, 4, 0, 6 out of the dictionary. And we're going to put it into our decompressed list. Awesome. We move on to the next number, which is 8. Well, we only represent 0 to 7, so it has to be in our dictionary. We go to our dictionary, and we see the number 8. 8 represents 0, 0 and 0, 1. So we add 0, 0 and 0, 1 to the decompressed list. 0, 3 is our last and next number, and it's not in the decompressed list, and it's not in our dictionary. So we write down 0, 3. And so what we've done is we've gone through the list of compressed numbers, and we create our own dictionary as we start decompressing it again, because these couldn't be compressed without making their own dictionary as well. And so when we've gone through and made our own dictionary later in the compressed list, we were able to find numbers which were attributed to the dictionary, and we were able to find their pairs. So for 11, we found 0, 4 and 0, 6. And then for 8, we found 0, 0 and 0, 1, which we were able to add to our decompressed list. And so in theory, what we just did is we just made the same string that we started with when we compressed it. So what we're going to do to verify that is take this number up top and see if it matches our decompressed list. The one on top will be our uncompressed, and the one at the bottom will be our decompressed list. So making sure they line up. 0, 0, correct. 0, 1, correct. 0, 2, 0, 4, 0, 6, 0, 7, 0, 4, 0, 6, 0, 0, 0, 1, and 0, 3. And so the LZW compression holds true. The way this compression works is it builds a dictionary to represent pairs. Whenever it sees that there's a pair, it uses the number in the dictionary, and then that runs to the end. It can only look forwards, can never look backwards. And then when it's decompressing it, it creates its own dictionary by the numbers that were not able to be compressed in the beginning, and then it uses its own dictionary, which it created in its own decompression algorithm, to decompress the larger numbers. And that's how it works.
Hello, my name is Gen Galshe, and I will be explaining the compress function in the LZW algorithm. I believe in the previous part, Alex has explained the main theory of the LZW algorithm, and in this part I will explain its actual Java implementation. So I divided the compress function in 3 parts to make it easier for the viewers to understand. The first part is the setup part. So this part, what this basically does, it allows us to input in the parameter only a string, or it also allows us to input a text file. So if we put a text file, this will check if it is a text file by checking the last 4 characters. Then it will use this convert file function, basically a helper method, which I created to convert a text file into a string. Then the next part is creating a standard character set, which represents the first 256 ASCII code characters. So here we just set the size of our dictionary to 256, and in our case we use a hash map. In the hash map we store a string and an integer. So we iterate over the integer 0 through 255, and for each integer we put inside the dictionary the corresponding ASCII character of that integer and that actual integer. Therefore, when we come to the number 65, we will put its corresponding ASCII character, which is capital letter A, and the number 65. Afterwards, we come to the actual algorithm part. This is a little bit more complicated, but it's not that difficult to understand. So first we start by creating a list of integers called result. This is the main output, the main value that we will return to the user. And for then we use the for loop to iterate over all the characters in the provided input string. Then for each characters we add the found characters and the current character to this string called chars to add. We use this chars to add, which is basically a concatenation of this character, of found characters and current characters. And if that character is found inside the dictionary, we will update found chars to store the actual character. Therefore, in the next iteration of the for loop, chars to add will represent the previous character, found chars, and will also represent the current characters. If we didn't find any entry inside our dictionary, we do these 3 steps to update our code, our result. So first we add the found chars to the result, to this list. Then we add a new entry to the dictionary for each character that we haven't been able to find yet. And in the end, we reset the empty string. By empty string, I mean this found chars, to point to the current character in that current specific iteration. And this simple algorithm will basically will compress our string. And there's one specific edge case where there is a chance that the last character that was a found character. And in that case, the for loop will end at the if statement right here, instead of ending at the else statement. If it ends at the if statement, it means that that found character will not be added to our result. Therefore, we created this simple if statement which checks if found characters is not empty, it will add that found character to the result, and in the end we just return the result. So that was the compress algorithm, and Fernando will explain the decompress algorithm. Thank you.
The decompression method works by taking the encoded text with the goal being to obtain the initial text that was originally compressed earlier. We start this by creating a dictionary size of 256 and a dictionary map using integers as keys and strings as values, which is done by the for loop below it. Next, we create a string called characters, which assigns the first integer of the encoded text and removes it. The first integer of the encoded list always represents the character found in the initial dictionary, so our resulting string will start with that character, which we will retrieve and remove from the list of integers passed to us as input. For the remaining integers, we are going to loop over them, and for each one we need to check if the key set of the map contains this particular code. If it does, we retrieve it, and if not, we take the first letter from the characters we just had in the previous iteration and append it to the same set of characters. Next, this retrieved entry is appended to the resulting string, then the first character of this entry is appended to the characters of the previous iteration and added to the dictionary to generate the same entries as the encoded text. Finally, the characters of the previous iteration are updated to reference the current one to be able to proceed with our loop and with the remaining integers. Lastly, we want to return the resulting string, which should be the initial string from the encoded method.
Okay, so this is an explanation of the decompression algorithm test that we have created, and I will be explaining the compression test portion of it, and later the decompression test will be explained towards the end of the video. So to start off with, this test is really made up of 3 small parts: generation of random strings, compression of said strings, and then testing to make sure that the file size is less than the uncompressed string. So to start off with, we create 2 different lists. One list of strings uncompressed, and then a list of strings compressed. And this is all integers right here through the compressed function that we've created earlier on. So this code right here is the code just to create a string. It loops 5 times. It makes 5 different strings, all 300 letters long, A through Z, and it's 300 so that we get a variety of letters and different patterns that it can test and check. Any less than like 150 and we might come up with some issues, so 300 is a pretty good number to start off with. And it's 5 times just so we have 5 different strings to test. These strings are then added into the list of strings uncompressed and later on compressed in the second part of this test. The test is looped 5 different times, and we have imported the algorithm that we created here, only the compressed portion, and it simply just compresses the array list of strings that we have made here, and adds it, the compressed version, to the list of strings compressed. Later on, next, we check, as I said before, if the file size is less than the uncompressed string. If this turns out to not be the case, then the test case fails, as there is no change in the string, in the file size. So it'll print out, did not decrease the file size, and then you just have to check and see why that is. If it does pass, then you just pass the test through right here. And it's not too bad. that'll be all.
All right, so this is the test method for the decompressing of the file. Basically, how it starts is we obviously generate the compressed string here with the test compress, and then we bring in a for loop where we assume that it passes all the cases and everything. Otherwise, that's when everything below happens. Here, the decompress string is created with the LZW algorithm as it compresses the list of strings compressed, and basically what happens is if the list of strings that are uncompressed equals, or it doesn't equals the decompressed string, then that means that obviously the string doesn't match, the cases are listed as false, and we break from it. Similar to if the same case happens with the file sizes. If the file sizes aren't the same between the decompressed string and the list of strings that are uncompressed, that's also a break. But assuming that those aren't the case and everything's true, then obviously we assert everything's true, the cases are passed. So basically what happens is for the entire compressed list, it goes in, it decompresses it, and then it checks to see if that decompressed string matches the one that wasn't compressed in the first place. So it does that for all of the strings that are in the list, and then if it never fails, and at the end it returns true and everything should be fine. So it's basically a test to make sure that everything comes in the same, and as we see with here, when we test that, bingo, works well. So yeah, that's the test decompress in full effect.
Hi guys, Alex here. So I'm just going to quickly talk about the last test method that we have for our LZW algorithm, and that's going to be the test file compression. So what this one does is it creates a list of files to compress, and there's a bunch of file locations in here. There's 5 files with all randomly generated strings. If I'm going to go into here and show you one of them, the compression files. If I open just one of these text files through Notepad, it is a massive string of randomly generated characters. And in here, the test just goes in, creates the compressed string and then the file strings to compress, and then it compresses the file. It uses the convert file method first from the LZW algorithm, then it compresses the file for each and stores it in the file strings compressed. And then we assume that the test passed everything, and then we go in and test each case, and if it fails any of them, we turn the condition to false, and we also fail the test. However, at the end of it, if we get through it all, then we assert true. So what we do is we check to see if when it compresses, the file size is less, because that's the goal of compression. And then when we decompress, we check to see if the length is the same, right? Because same words should have the same value. And then we check to make sure that the words are actually equal to each other. And that's really all there is to the convert file compression test. It just uses the convert file and then runs the rest of the compression test like before.